Today I'm going to explain how the loop-the-loop problem works. So it's basically like a sphere, so falling down the track, and then it's doing a circular motion. Basically that. And then let's see what's going on here. First of all, for the loop-the-loop problems, this metal sphere is falling from a track, and then doing a loop. So it's doing a circular motion. So if you draw a free body diagram, you know that there's two forces acting on the sphere at the top. So there's a weight and there's a normal force. I have not drawn the normal force because these two forces add up equals to the centripetal force, which is required for the sphere to form a circular motion. So there's a minimum speed for the sphere to have, which is when the normal force equals 0, which means that this metal sphere starts to lose contact with the track. So there's a minimum speed required, which is, now it becomes mg equals mv squared divided by r, which this is the minimum speed required. So assuming there's no rotational motion, for example, let's say this is not a sphere, this is a block. So when the block is falling from the top of the track and doing a circular motion. So there's no rotational kinetic energy, so we have mgh, which is gravitational potential energy stored here, which equals to the linear kinetic energy, which is here, and also take a look. There's a height which is 2 times the radius. So r is the radius of the loop. So finally we get this formula. So h equals to 2.5 r. And remember, we're assuming there's no rotational kinetic energy, but this is not true because we're talking about a sphere. So sphere will rotate, which means that there must be a rotational kinetic energy. So assuming it's a sphere, so now we have gravitational potential energy stored here. So that's a gravitational potential energy, but also there's a linear kinetic energy, there's a rotational kinetic energy, and that's the gravitational potential energy stored by the sphere when this sphere is at the top of the loop. And mgh now equals this. Now look at this. So 2 over 5 mr squared, that's the moment inertia of a metal sphere. Assuming that there's no slipping, rolling without slipping, so omega equals to v divided by r, so omega squared equals v squared over r squared. And finally we get h equals 2.7 r. So assuming that's a sphere, we can later test whether this is true or not. So first of all, we measure the inner diameter, which is roughly 13.5 centimeters, and also this sphere approximately diameter of. I'm making a rough measurement, which is roughly 2.5 centimeters. Remember, I'm doing a quick measurement here. So, so the ball actually, the center of mass actually moves. So this diameter d minus the diameter of the ball, which is 13.5 centimeters, which is the internal diameter of the loop, minus 2.5, which is diameter of the sphere, because the center of mass moves d minus the diameter of the ball, which is roughly 11 centimeters, which I'm making a very quick measurement, so I have an uncertainty of plus or minus 0.5 centimeters. The diameter of the ball is 2.5 centimeters. Now, let's first of all assuming there's no rotational kinetic energy. So this is 11 centimeters times 2.5, as we have predicted. If there's no rotation, that's roughly 27.5 centimeters. So right now, let's make a measurement. So that's a roughly 28, because there's a 0.5 centimeters at the beginning. So that's roughly 27.5 centimeters. Let's try. 3, 2, 1. You can see that it cannot doing a full circular motion. It falls somewhere here. So now let's consider there's a rotational kinetic energy, which is 2.7 R. So 2.7 times 11 to give me 29.7 centimeters. So I have to change this to 30, or roughly 30.5 centimeters, because there's a 0.5 centimeters at the beginning. Or you can call that systematic error. So right now, let me measure it again. So this 31 centimeters minus 0.5, which is roughly 30.5 centimeters. Let's try again. You see that now it can almost do a circular motion, probably 99% circular motion, and without losing contact with the loop, because there are some friction force or some energy loss.